Was that too fast? What we always do in science is repeat the experiment. So I take out what looks like a dollar bill, but it's not a real dollar bill. I bring it close to the flame. Disappears into thin air. It looks like magic, right? I love magic. Magic is engaging, but not informative. So I'm going to take this liquid, and so I want everybody to see the jar right here. Get this out of the way. I'm going to take the dollar bill. I'm going to soak it in this clear and colorless liquid, which looks like water. And I'm going to fish it out using those tongs. You see it's dripping like any wet object would, right? And then I'm going to take it to the flame. Take a good look at it now, Judy. It's maybe the last time you see it. So here is the dollar bill on fire. Or is it? But you did see a flame, didn't you? So now I ask you, can this liquid be water? You know from experience that water does not burn under these conditions, right?
Call it money to burn. How was that dollar bill burning up so quickly? Well, it's actually not a real dollar bill. It's called flash paper. It's a paper that has been treated with chemicals to burn quickly and leave no ashes. Flash paper has been nitrated. Actually, you soak the paper into a concentrated mixture of nitric acid and sulfuric acid. Then, cellulose in paper reacts with acids to produce nitrocellulose and water. The reaction is this. We know NO2 is a reactive group which makes molecules explosive. Then, we'll see that the doctor uses real dollar bills. Okay, what happened there? The doctor soaked the paper in a solution of water, rubbing alcohol and a little bit table salt. Then, put the dollar into flame. The alcohol burns, producing heat, light, CO2, water, and energy. The reaction is this. So, why doesn't the bill burn? First, it's important to claim that if you light a glass of alcohol on top, only the top layer of alcohol and the gas above will burn, and no other alcohol in the beaker will. So, it's similar to the situation of the dollar bill. The alcohol is evaporating off the bill, turning into the gas, and burning. Then, you see the flame, but just 50% water, and the water stays in the bill and prevents the bill from burning. So, that's why the dollar bill doesn't burn. This is what's so-called money to burn. I hope you like it.
I'm going to take chunks of dry ice and put them in the cylinders in a very special way. And when I get done, you tell me what the special way is. What's blowing out? You see any bubbles? I want you to focus your attention on this one and tell me, count them out, how many different color changes you see as I drop the dry ice in there. I'm listening to you on the radio. 1. Wow, I heard wow. What kind of a count is that? 3 so far? 3 different color changes.
Colorful indicators. Alright, let's break down what's happening in these cylinders. There are 6 of them, and each group's color is different because there's different acid-base indicators inside them. The leftmost ones are blue, then pink, and the final ones are purple. And every cylinder contains a few drops of sodium hydroxide, which is a base. NaOH is a base. So, let's start with the basics. What is the acid and the base? One definition is that acids are compounds that donate a hydrogen ion, or H+, to another compound, and the compound accepts the hydrogen ion is a base. Okay, Let's back from the cylinders. The first set of cylinders contains indicator bromo-thymo-blue. Let's take a look at the spectrum. Alright, so let's take a look at bromo-thymo-blue, the indicator in the first set of cylinders. As you can see, here's some scales of number, which is pH scale. The higher the number, the stronger the alkalinity. The lower the number, the stronger the acidity. Our solution starts off basic, which is blue and contains NaOH, and this is what chemical structure of the molecule looks like when it's blue. The chemical bonds in the molecule can absorb visible spectra other than blue. So, the blue is reflected back to our eyes. But if the compound binds to a hydrogen ion, the molecule will change color. Now, it starts to absorb blue and reflects yellow. Okay, now let's take a look at what's happening in the middle set of cylinders, which is pink. The indicator in there is phenolphthalein. The situation is quite similar to bromo-thymo-blue, but this time, when the solution is basic, it's pink, and when it's acidic, it's colorless. But why does the solution change from basic to acidic when we add dry ice? Because dry ice is solid CO2. When we add it to water, the CO2 will dissolve into the solution. Then, this will produce carbonic acid. Let's look at the equation. The acid reacts with NaOH and finally the solution becomes acidic. So, we can see bromo-thymo-blue changes color from blue to yellow, and the phenolphthalein changes color from pink to colorless. Okay, let's watch again what's happening in the final set of cylinders. Okay, in the final set of cylinders, the doctor uses the mixture of indicators. We can see 3 changes of color. First, from purple to blue, then to green, finally to yellow. So, that's all. I hope you like it.